Assalamualaikum and very good day. So today we're going to proceed with a new chapter, which is chapter 5. So in chapter 5, we will learn about Reynolds number, laminar flow, and turbulent flow. Okay. So basically in this chapter, okay, I will discuss with you, okay, how can we use the parameters which is called as Reynolds number, okay. The Reynolds number is actually the dimensional parameter, okay. So based on this Reynolds number, okay, we can categorize whether the fluid is flow under laminar or turbulent flow. Well, at the end of this session, okay, you will be able to know how can you calculate the Reynolds number of the flow, okay, in two categories of condition, okay. So the first one is you will learn how can you calculate the Reynolds number, and after that you will know based on the Reynolds number whether it is turbulent or it is laminar category, okay, if the fluid it is in a round pipe. And second outcome that we expect you to gain at the end of the session is you will also to able to calculate the Reynolds number for the flow which is in non-circular section, okay, in which that for the second part which is in non-circular flow, okay, you need to use another additional parameter which is called as hydraulic radius. Okay, let's check it out. Okay, so here is the topic outline which is available in this chapter. Okay, so basically I have divided into three main parts. Okay, so the first one is we will discuss about what is the Reynolds number and how can we use this parameter in order to categorize the flow. Okay, and the second part in which that we will learn about the velocity profiles for two types of the flow, which is laminar flow and turbulent flow. Okay, and the last part is we will learn how can we determine the Reynolds number, okay, in non-circular section, okay, because this one is quite different from the first one, because the first one is we focus on the round pipe, okay, but the third one is only for non-circular section. Okay. Okay, let's proceed with the first part, okay, in which that we want to know how can we calculate the Reynolds number, okay, and based on the Reynolds number, we will determine whether it is laminar or turbulent flow. Okay, I just want to remind you again, okay, for the first part, we just focus the flow which is involved in a round pipe, okay. Okay, so before we learn into detail about the Reynolds number, okay, it is worth for us to know what is actually laminar flow and what is actually the turbulent flow. Okay, so based on this diagram here, if you look at the diagram here, okay, so basically it shows us kind of simple experiment conducted in a fluid inside this pipe, okay. So basically it just injects some dye injection tube, and basically this is a fluid. For example, you can imagine that this is water flowing inside this tube, okay, and you also inject dye here just to not give some just to give kind of color so that it will be easy for you to recognize the types of the flow, okay. So if it's laminar flow, okay, there will be no mixing fluid across the boundaries for each layers of the fluid flow through flows along the path. Okay, so as you can see here, the flow is it is just like there is no mixing between the streams. Okay, but for turbulent flow, okay, if you look at this diagram here, okay, once you inject the color, okay, the dye inside the flow, okay, you can notice that, okay, the flow is not synchronized, okay, or we will say that it is appears as a chaotic and rough with much intermixing the fluid, okay, or the easiest way to understand it, okay, you can just imagine that if you sit by near to the beach which has lots of rocks on it, okay, so the turbulent flow is some the flow which is that like when it's a wave, huge wave comes near to the beach and hit the rock, so it will appears like a chaotic uh, kind of flow, okay. But for the laminar flow, it's more like very calm flow, okay. Usually you will see that this kind of the flow which is near in the river or the lake, something like that, which is no big wave or something. All right, I hope you clear about the characteristic of the flow between the laminar and turbulent flow. So why it is important for us to know whether the fluid which is under categories of laminar or turbulent flow? Well, it is actually very important because the fluid behavior or the fluid characteristic is actually influence the amount of energy losses in a fluid flow system. Okay, so how can we categorize between the laminar and turbulent flow? Okay, as I mentioned just now, okay, the prediction of laminar and turbulent flow, okay, can be done by using the Reynolds number. Or in other ways, I will say that based on the Reynolds number, then you will know whether it is turbulent or it is laminar. Okay. So this is the formula to calculate the Reynolds number. Okay, so this is rho times with velocity u and the diameter of the pipe divided by kinematic viscosity. Okay, or sometimes you can also um, use this term. Okay, you can the formula can also be rewrite into this term, which is the v here is actually v equals to the ratio between density divided by kinematic viscosity. Okay, so for the flow inside the pipe, okay, we will know whether it is laminar or transition or turbulent flow based on the value that you calculate here. Okay, so for example, if your Reynolds number falls which is less than 2000, it is categorized as laminar. Okay, and if it's more than is in between if it's between 2000 and 4000, okay, it is categorized as transition flow or critical region. Okay, and if it's bigger than 4000, it is categorized as turbulent flow. Okay, and sometimes this formula also can be rewrite into this form. Okay, so the difference is only the notation here, because sometimes in certain of book they rather use a v instead of u, okay, to represent the velocity, but both are the same, which is both are velocity. Okay, okay. Okay, so let's try with this first example. Okay, so based on the question here, the question said that determine whether the flow is laminar or turbulent if the glycerin at 25 degrees C flows inside a pipe which is the inside diameter is 150 millimeter and the average flow velocity is 3.6 meter per second. Density and dynamic viscosity of the glycerin are 1258 and 9.6 times 10 minus 1. Okay, so first of all, we have to extract the information or from the equation first. Okay, so the equation asks us to know, okay, it wants to know whether it is laminar or turbulent flow. So how? We have to calculate the Reynolds number. Okay, then from here we will know whether it is laminar or turbulent flow. Okay, so the categories of the fluid here, okay, the fluid is categorized as glycerin. So we have glycerin, in which that the temperature is 25 degrees C. Okay, and it flows inside a pipe. So the diameter of the pipe is 100 millimeter, and we change into SI unit 0.15 meter. Okay, and the average velocity of the flow, the velocity is 3.6 meter per second. Okay, density and dynamic viscosity. Okay, so density here, which is 1,258, and the viscosity is 9.6 times 10 minus 1. Okay, so this is the information which is provided from the question. Okay, so let's check it out. Okay, how can we solve this problem? Okay, let's check it out how to solve the problem. Okay, so we know that our objective is we want to know whether the flow is laminar or turbulent. Okay, so first thing is you need to provide information provided from the question. You list down all the info provided from the question, and you also need to have kind of formula plan. Okay, so definitely the question asks you to determine whether the flow is laminar or turbulent. So in order to determine whether it is laminar or turbulent, it is based on the Reynolds number. So that's why the equation that you need to use is this one. Okay, so this is my equation plan. Okay, so what is the information provided from the question? Okay, let's check it out one by one. And for example, this one, in this case, the diameter is provided, which is 150 millimeter. Okay, so which is, I write it down in SI unit, which is 0.15, and velocity, which is 3.6 meter per second. And for density and viscosity is not provided, but this info is needed to solve the equation. Okay, but the solution did provide us information about the fluid, which is it is glycerin and flows at 25 degrees C. So that's mean you can get this information, these two information, okay, from appendix table. Okay. Okay, so as I said just now, we need to determine what is the density and viscosity of the glycerin at 25 degrees C. Okay, so for example, here we have glycerin, and of course this table is actually at 25 degrees C, so we can get directly the value from this table. Okay, so it is glycerin, in which that the density is 1.258 and the viscosity is 9.6 times 10 minus 1. Okay, so just substitute into the list info that you have before. Okay, so I repeat again. So first, list down the info from the question, and you notice that you have two information, which is you need to get it from the table appendix or appendix. Okay, so next proceed to the next step, which is you need to get the info from the table. Okay, so based on the appendix that I showed in previous slide, so we already have the information about density and also dynamic viscosity of the glycerin at 25 degrees C. Okay, so we already has all the information which is needed in order to solve this equation. Okay, so just substitute the value into the equation in order to solve the value of Reynolds number. Okay, so after substitute into the formula, in this formula, okay, we will get the Reynolds number, which is at 707.63. Okay, so if you check again with the categorized for the turbulent and laminar flow, okay, so this number is actually less than 2000. So it is laminar flow. So that's it. We already solved the question. Okay, let's proceed with the next part, which is in this part, we will learn a bit, okay, about the velocity profiles for turbulent and laminar flow. Okay, so if I relate back with the previous chapter, is we want to know what categories of that flow. Okay, so in this chapter we will check how is the velocity profiles. Okay. Okay, so our aim is we want to check what sort of the velocity profiles in laminar and the velocity profiles for turbulent flow. So here is, I repeat again, how the flows looks like in a laminar flow. So for example, this one here, as I mentioned in the previous slide, okay, when we inject the dye, okay, inside the pipe, which is the flow is laminar, it's kind of uniform flow like this. Okay, so how the velocity profiles looks like. Okay, and for turbulent flow, okay, if we inject the dye, okay, it will looks like this. The flow will look like this, like chaotic flow. Okay, it's not uniform like this. Okay, so if you can see, it's become, like that. Okay, but this one is just smooth type of flow. Okay, so how the velocity profiles looks like. Okay, so if you check here, okay, the velocity profiles is kind of reduced, which is in the area which is near to the surface of the pipe, but it will increase when it is in the middle of the pipe. Okay, why? So of course it relates back with maybe like friction near to the surface of the pipe. Okay, and because it is low, so that's why it can interfere with the friction. Okay, so therefore the laminar flow will made up of fluid or streamline in which that the momentum transfer between molecule is less and the velocity profiles becomes parabolic. So if you can see here, the shape of the velocity profiles for the laminar flow is parabolic, in which that it reduces, which is near to the surface of the pipe, and it will increase in the middle of the pipe. Okay. Meanwhile, for turbulent flow, it will look like this. Okay, it's kind of uniform. So what happened is, in the turbulent flow, more uniform velocity distribution profile for turbulent flow because there is a transfer of momentum between molecules during chaotic motion and violent mixing of fluids. Okay, because as you can see here, because due to the chaotic condition, so that what happened is there's a transfer of momentum, okay, between the fluid that make it the velocity profiles become like this. Okay, all right, that's it. Okay, so why it becomes like that? Okay, so as I already explained a bit before, in which that in a pipe with turbulent flow, okay, there is exists a thin layer of fluid near to the pipe where the velocity is quite small and in which the flow is actually laminar. Okay, so at that area, there is a condition we call it as a boundary layer. Okay, so in this boundary layer, okay, so what happened is the regularity of the velocity profile in laminar flow has enabled the definition of equation for the prediction of local velocity at any point of the flow. Okay, so remember that if the pipe like this, okay, so when there is a velocity profile, okay, in that pipe, okay, so actually the size or the condition of the pipe or the flow inside the pipe may influence the velocity profile. Okay, so if you want to determine the local velocity of the flow at any point, okay, so you can use this equation, which is u equals to 2v times 1 minus the ratio between maximum and minimum radius, okay, and the power of 2. So you can get directly what is the local velocity at any point. All right. Okay, last but not least, we will come to the last part, okay, in this chapter, which is flow in a non-circular section. So what does it mean by flow in the non-circular section? Okay, so if before this we keep on determine the Reynolds number of the flow, that one, the Reynolds number rho v d divided by mu, that one is for circular section. So what if the flow inside the part which is not circular? For example, maybe it like in the shape of rectangular or whatsoever. So how can you determine what is the Reynolds number for that flow? Okay. All right. So in order to determine the Reynolds number in an area in which is non-circular area, so there is a method to do that, okay, in which that we need to use the hydraulic resistance, sorry, hydraulic radius, okay. So if you still remember, the Reynolds number formula is rho vd divided by mu, okay. So now this d, which is no longer can be used because the pipe is no longer circular, it is non-circular shape. So this d parameter need to be replaced with this new parameter, which is called as hydraulic radius. So what is hydraulic radius? Okay, so hydraulic radius is actually, we can determine it, okay, by using this formula, which is the ratio between area and the wetted perimeter. So what it is, okay, let's take a look in the next slide. Okay, as I mentioned before, for non-circular section, we use this formula, which is that this is additional term in which that we replace the terms of D in the normal formula for the Reynolds number, okay, which is R is actually the referred as the hydraulic radius, okay. The hydraulic radius is actually the ratio between area and wetted parameter. So what is actually wetted parameter for the non-circular section, okay? So here in figure A, B, C, and D, okay, there are four types of a non-circular section. So actually, if you can see here, the shaded area is actually the area where the fluid flow through it, okay. So for example, like this, it's kind of shaped like this, okay, and this is like in rectangular shape, and this one as well is non-circular shape, and this one this there is a hole in the middle, okay. So for each categories of shape, okay, it has its own formula to calculate the area and the wetted parameter, okay. So for example, this is for A, and for B, this is the way to calculate the area and wetted parameter, okay, C and D, okay. So just take a look at the diagram and the symbol of the dimension, which is referred inside the formula here, okay. So you can just substitute it and get what is the A and WP, and once you have the A and WP, and you can calculate the hydraulic radius, okay. So basically, the wetted parameter is actually refers to the sum of length of the boundaries of the section actually in contact with the fluid, okay. So this is very important. Okay, so let's try example in which how we can calculate or categorize the types of the flow in a non-circular section. Okay, so by referring to this question, okay, let's read through the question. Okay, so it says that determine the Reynolds number for the flow of ethylene glycol at 25 degrees C that flows through non-circular section as shown in figure 1. Okay, which is figure 1? Okay, here is the figure 1. Okay, so the flow rate of the flow inside this non-circular section here is 0.16 meter cube per second, and dynamic viscosity and density of the flow are 1.62 and 1100. Okay, so this info is given. And it is known that the inside dimension of each side of the square is 250. So that means the S is actually 250 millimeter. And the diameter of the tube is the tube here is actually 150 millimeter. Okay, so this info is actually mentioned in here. Okay, so how can we solve this problem? Okay, let's solve the problem. Okay, in which that in this question we need to solve what is the Reynolds number for the flow, which is the fluid is ethylene glycol in a non-circular section. Okay, as usual, as I always told you, the first thing first that you need to do is list down all the info provided and plan your formula to solve the question. Okay, so here is the information that we extract from the question, in which that the question still need you to determine the Reynolds number, okay, in order to know whether it is laminar or turbulent, okay. And we know that the fluid is actually the ethylene glycol at 25 degrees C, okay. And it is flow through the non-circular section, in which that the diagram or the figure of the flow inside the non-circular section is given. Okay, so this is the shape here. Okay, and the information or dimension of the shape is given as well. For example, the side dimension is 0.25, the inside diameter is 0.15 meter, and the question gives you flow rate, okay, which is 0.16. But the velocity is not given, but actually you can get calculated, okay, the velocity based on the information from the flow rate and the area. And density, well, in this question the density is given, and so do for the viscosity is also given. Okay, so this information is given, so you don't need to get it from table or appendix. Okay, but in case if it's not given, you can get it from the table by knowing that it is ethylene glycol at 25 degrees C. Okay, let's proceed and solve the problems. Okay, so definitely we have to use this information, this formula. Okay, so if you can see here, we have new additional parameters here, because usually the normal one for the circular section, this one is actually the Reynolds number is actually rho Vd divided by mu. Okay, but for the non-circular section, this term is actually replaced by the items of 4r here. Okay, so let's plan our formula. Okay, so definitely we need to know what is the r, which is the hydraulic radius for this shape. Okay, so this shape, how can we get the hydraulic radius? So the hydraulic radius is actually a ratio between area, which is being flowed by the liquid, and divided by weighted parameters. Okay, so this is the area that you can calculate, okay, for this type of shape. So you can just substitute it using this item, and same goes to the WP. Okay, just use this one. And for the area, okay, so the same, I just took it from there. Okay, and then next is for WP. Okay, I just got as well from the figure. Okay, and for the U is velocity. As I mentioned just now, we don't have information about the velocity, but we do have information about the flow rate. So the flow rate can be used to calculate the velocity, in which that you can use the Q divided by A, and again the A, you can just use the same A that you use to calculate the hydraulic radius. Okay, so since that we already have all the needed information to be substituted into this formula, so we can just substitute all the value into the parameters. Okay. Okay, so after we substitute all the parameter, you will be able to get the Reynolds number. Okay, so this is our Reynolds number. So I just recall back what we planned from the previous slide, in which that we want to determine the Reynolds number. Okay, so definitely we need all the information included here. For example, we need velocity here, okay, and then we need the area. The area we already calculated here, and we need the weighted parameter. What parameter is this one? And we also need the R, the hydraulic radius, this one. And lastly, we can substitute into the formula, okay, since that rho, the density, and viscosity is given in the equation. So we just substitute all the information. And lastly, we get this Reynolds number, which is 29,000, about 29,000. So from that, we can make a conclusion in which that because it is greater than 2000, so it is turbulent flow. That's it. We're done with this question. Okay, that's it for this chapter. Okay, so see you in the next chapter. Hope you can use the video given in order try your best to understand about this topic. Good luck. Thank you very much.